What is up, VCE Methods students? Today we're going to go through some integration rules. Integration rules is nothing that you have to memorize. It's all on the formula sheet, but with practice, you're just going to memorize them anyway, and you're just going to get used to them and just, remember the rules and make it faster for yourself. We don't want to always go through the formula sheet whenever we're, solving equations and, solving these honestly basic questions when you get to your final exam, but they are there for reassurance anyway. So just know that you don't have to necessarily memorize them, but with a lot of practice, we're aiming to be, top 10%, top 5%, even top 1% student, you're going to eventually memorize them anyway. So let's get started. And you'll notice that all of these rules are pretty much the backwards of differentiation anyway, because as I've reiterated in previous videos, integration is just the opposite of differentiation. So for example, we have this power rule here. So you can see that x to the power of n becomes where you add 1 to the power and divide by that new power. If you think about the differentiation rule, you multiply down by the power and you minus 1 from the power. So you can see this is just the opposite thing in the opposite order. I'm just going to quickly describe to you how the notation for integration works. So you have this squiggly line here. So this is kind of like the integral operator. So whenever you see this, we're finding an integral. So in this case, how we read this is the integral of x to the power of n with respect to x. So dx just denotes what the independent variable is that you're integrating with respect to. It's very similar to the d over dx for differentiation. So the integral of x to the power of n with respect to x. So you can see, as I said before, you add 1 to the power and you divide down by that new power. The only addition is the plus c here. And again, these are just the general rules, so that's why we include the plus c. And as I said in previous videos, if you have an extra piece of information, such as a coordinate that lies on your function, then you can substitute in that value and you can find the specific c value for that case. In these cases, we don't have an individual point, but if you were given one, then you'll just substitute it in to find the c value. So let's try and evaluate this one. We have the integral of x squared plus 2x cubed dx. Now, very similar to differentiation, if you have two individual functions added together, then we just find the integral of them respectively and then add the two integrals together. It's not too complicated. So in this case, we have x squared. So if we want to integrate that, what do? We add 1 to the power, we divide by that new power. So this one is going to become x cubed over 3. Now for 2x cubed, we add 1 to the power, so it becomes 2x to the power of 4. Then we divide by that new power, so this one will become 2x to the power of 4 over 4 plus c. The only difference we have in this case is we have to simplify this one, so that will become x to the power of 4 over 2, and that's going to be our final answer. Now, here we have a different type of rule. This one is just a normal power rule. This is a very specific rule. And the reason why we have a very specific rule is because integration is more complicated than differentiation from a calculus and an algebra standpoint. So you might actually notice that this is very similar to the chain rule. This is just the backwards of the chain rule, but the chain rule in a specific case where you have something linear raised to a power. We actually don't have a general chain rule that we learn in VCE methods. We just have this specific case because it's a bit more basic and it's easy to apply the formula. But for other things in chain rule, let's say if you have just a function inside another function, let's say you have log base e of cos of x, there's no general rule for that. That's really easy to implement in VCE methods. So it's actually reserved for later maths. Let's say if you're doing engineering in university, you'll learn about your general types of chain rule and that type of thing. In this case, we don't worry about it. We just have a specific rule for this specific case that is a bit more common in VCE methods compared to other cases where you just don't need to know it. So in this case, we have ax plus b to the power of n. If we want to integrate that, what you do is you divide by the coefficient of x. So you can see that's a there, divide by the new power, which is n plus 1, and then you just have ax plus b raised to a new power. And it's exactly the same for all the other integration rules. If you differentiate this function, you're going to get your original function back. So that's a good way of double checking when you're first learning integration. It's that you can just reverse the process and you can get the original function back. And it's a really good way of double checking if you've done things right. So in this case, we have the integral of 2x minus 1 to the power of 5. So if we just apply this formula, we have 1 over the coefficient of x, which is 2, and then 5 plus 1, which is 6. Then our bracket remains the same, and the only thing that changes with our power is we just add 1. So this one will just become 1 over 2 times 6, which is 1 over 12. And that's pretty straightforward there. Okay, so for this rule here that we discussed before, this actually works for most cases. It works actually for all cases except n is equal to -1. And there's a couple of reasons for that. One of the main reasons is that if n is equal to -1, you can see that we divide by 0 because -1 plus 1 will equal 0. And you can see also if we have -1 there and then you have a new power, the power is going to equal 0, which doesn't make sense. Power equals 0 after you add 1 to make the new power. So if n is equal to -1, we actually have a specific case, and you might notice here that I've kind of emphasized this, n is not equal to -1. So this works for all n values except -1. So when n does equal -1, we actually have a separate case altogether that is separate on the formula sheet as well. And you can see when n is equal to -1, this can actually be simplified to 1 over ax plus b, because whenever you have a negative power, you can bring it at the bottom. So it's going to be 1 over ax plus b to the power of 1. And obviously the power of 1 doesn't make a difference algebraically. So what you actually do in this case is you memorize a new rule, and this new rule is 1 over a log base e of ax plus b plus c. Now, if you look at the formula sheet, depending on which formula sheet version you're looking at, and depending on what textbook you use in class as well, your formula sheet might actually split this into 2 equations. And the reason why it splits it into 2 equations is because ax plus b can't actually be negative. And that's because you can't have negative values inside your log bracket. So there's 2 ways of overcoming this issue. The first way is to split this up into 2 formulas. So let's say if ax plus b is greater than 0, then this formula is fine. But let's say if ax plus b is negative, let's say you're on the negative portion of your hyperbola, what you actually do is you say 1 over a log base e of negative ax plus b plus c. And we use this formula when ax plus b is less than 0, because what's going to happen is this is negative when ax plus b is less than 0, and then the negative at the front makes that negative positive because of the double negative property of it. Therefore, this bracket in total will be positive and the log can be calculated. Now, this is not the most ideal way of doing this formula. What I'm actually going to do is get my eraser and fix this up, because I don't like memorizing 2 equations, Memorizing 2 equations is a bit of a pain, okay? And I don't like to do more work than is required. So what I'm doing, sorry, this whiteboard marker is very persistent. What I'm doing is I'm making it easier for myself. I'm going to include these straight brackets here. You might not have seen it. You'll notice this, you kind of memorize this or find this familiar if you did SPECH. What this is a modulus bracket. So what a modulus bracket does is if the number inside it or the expression inside it is negative, it makes it positive. And if it's positive, it just stays the same. And this is very useful for log equations because you can only have positive values inside. So let's just do a basic example. If you have the modulus, so this is the modulus of -2. Again, it's just straight brackets. Modulus of -2 becomes 2. But the modulus of 3 will stay 3 because it's already positive. And again, this is very useful because let's say if this ax plus b expression is negative, it makes it positive and it makes the log actually useful and calculatable, okay? And if it's positive, it'll remain the same, so this is fine. This works for all cases of ax plus b, and you don't have to worry about memorizing 2 different equations. Now, just to let you know, these aren't all the equations that you have to use and memorize in integration for VCE methods. There's a whole list of them. It's not that long, but you'll notice that the list is actually smaller than the differentiation list. And the reason for that is because integration is more complex than differentiation, as I mentioned before. So therefore, there's less formulas that you actually have to memorize. So for example, you don't have to know the integral of log. You don't have to know the integral of tan, and there's no rules for chain rule, product rule, or quotient rule. And I mean, the only exception to that is this specific case of chain rule that's easier to calculate. There's no chain rule, there's no product rule, there's no quotient rule in general in VCE methods. So there's less formulas that you have to memorize, and obviously it makes it a lot easier when you've done differentiation before because the formulas are directly linked, because it's just the opposite of the differentiation formulas as well. Great, so now that we've perfected integral rules, we're actually going to move on to something called definite integrals, which is changing our integral into a specific number by substituting in values. Now that might sound like a lot of gibberish to you, but let me try and explain. This is what we know so far, right? The integral of x squared with respect to x becomes x cubed over 3, and that's due to the power rule. Now this is what we call an indefinite integral, okay? So I'm going to say indefinite integral. That's the terminology that we use for just when we integrate a function and get another function back, okay? And the reason why it's called indefinite is because it's not happening over a certain x value. It's the same as if you have a function and you differentiated it, you can get a rule, but then you could also substitute in a number to get a rate of change. There's just more specific terms in integration compared to when we do differentiation. So the indefinite integral is literally just a rule, okay? So if you ever see the term indefinite integral, just think of the rule for the integral. Now, a definite integral comes from the fact that we substitute in numbers, but it's different to differentiation because for integration, we actually substitute in 2. For differentiation, we only substitute in 1. So integration, we substitute in 2 values. Now, how do we kind of deal with that? We always substitute in the top number and then minus the substitution of the bottom number. So these are called, I mean, the technical term, I've never heard any other student call it this, but it's called integrands, okay? But you don't have to know that. You just think about it as the lower bound and the upper bound. So this is the lower bound, obviously, because at the bottom. This one is the upper bound. So I'll just write upper up there. Okay, so you substitute in the upper bound and then you minus the substitution of the bottom bound. Now, the most important thing to understand is obviously how we do it and the notation that we use. So the notation that we use is we use square brackets to denote what the indefinite integral is, and then we write the top and the lower bounds. So what we do in this case is the integral of x squared we know becomes x cubed over 3. So we put x cubed over 3 into the square brackets. Now we forget the plus c for now, and I'll show you why at the end. And then at the end of these square brackets here, we put -2 at the bottom, 3 at the top. Same as there, but we just put on the outside on the right. Now we substitute in the top bound minus the substitution of the bottom bound. So this becomes fairly straightforward. We get 3 cubed over 3, and then you minus -2 cubed over 3. And from here, it's just algebra. 3 cubed is 27, divided by 3 is 9. -2 cubed becomes -8 because it's a negative to a power of an odd number. So multiplying a negative number 3 times keeps it negative. So it becomes minus and then -2 cubed, which is 8 divided by 3. Now I can combine these terms together. 9 becomes 27 on 3. So 27 minus 8 is 19 over 3. Cool. Now, 19 over 3 is our definite integral. As I said before, we don't include the plus c, because if we included a plus c here, what would happen? I may use a different color actually. If we include a plus c there, what would happen is we have plus c there, and then when you minus this bracket from this bracket, the c's always cancel out anyway. So it doesn't matter what the constant is when you're doing integration or when you're doing definite integrals, the c's always cancel out. And even if you actually knew the c value, remember how I said that you can actually find the c value sometimes if you're given a coordinate or an extra piece of information? Even if you had one, for example, if it was 3, if it was -5, if it was 100, it wouldn't make a difference to our calculation anyway. So it doesn't matter what that is, you just ignore it whenever you're doing definite integrals. And just to reiterate, indefinite integral is the rule, this is the definite integral, and it's a value, okay? It's a value. Now, in the next topic, we're going to learn a couple of applications for integration, namely areas. Areas is the most common application for integration. Now, when you do that, you notice that when we calculate areas, you'll notice in the future, that you use unit squared as the unit when you calculate areas. So for example, if you find the area is 5, you write 5 units squared. It's really good practice, and you're probably not going to get full marks if you don't include the unit squared as a part of your answer. Now, the reason why I mention that now is a lot of people would then go back in time and calculate definite integrals, and they're going to write unit squared here, especially if you've already done integration before, and let's say you've done it in specialist maths or something like that. A lot of people would calculate definite integrals like this and then write 19 over 3 units squared. Now, that's not correct, because this is not specifically asking for an area. This is just saying to calculate the integral from -2 to 3, or the definite integral from -2 to 3. So it's actually not correct if you write unit squared when you're not specifically calculating the area. And I just wanted to kind of separate that out into 2 separate ideas before we move on to area and before we start kind of confuse them and kind of blur those 2 topics together. So here's where things get a bit more fun in integration, and you might not believe me because you might not find maths fun at all. But trust me, this application is very interesting and very useful in methods and just in day-to-day life as well. I'm just joking, it's not that useful in day-to-day life depending on what you do, unless you want to find areas under curves for fun. And that's what we're learning today. We're going to try to find the area underneath curves. And you might be thinking, what's the area underneath the curve? Doesn't it just go all the way down to the abyss in y is equal to negative infinity? Actually, no. The area under the curve is kind of deceiving in terms of its terminology, but if you have the area under the curve, what it's talking about is the area bound by the curve and the x-axis. So you can see the area that I've shaded here. It's between the curve, the x-axis, and the x values a and b. So a is what we call our lower bound, b is what we call our upper bound. And if we wanted to find this area, an expression for it would be the integral from a to b of f of x dx. Now, a lower bound, b upper bound, you might not be familiar or you might not remember what these bounds are actually doing. So what this is a definite integral. Definite integral, just as a reminder, is when we actually substitute in bounds to our expression. So what we do is we substitute in this into our integral, and then we minus the substitution of that one. And the difference between those two values is what we call our definite integral, and in this case, it's going to give us our area. Now, to actually illustrate how it's applied, what we've got is this really basic example where we have the function f of x is equal to x squared, and we want to find the area bound by the curve, the x-axis, and from x equals 0 to x equals 2. So how we do this is exactly the same application of this formula. What's the lower bound? It's x is equal to 0. What's the upper bound? X is equal to 2. And don't forget, you put the x values only, the y value doesn't really matter. That's kind of taken care of when we substitute it into our function. Now the function rule here, in this case, is x squared dx, and we just evaluate this. So how we go from this step to the next step is we find our general rule for the integral. In this case, we add 1 to the power, divide by that new power. We end up getting x cubed over 3. And you put your lower bound on the bottom of that square bracket, and you put the upper bound on the top of that square bracket there. Now from here, what we do is we substitute in the top expression, or the top value, and minus the substitution of the bottom value. So in this case, it's 2 cubed over 3. So 2 cubed is 8 divided by 3. And then we have 0 cubed over 3, which is obviously just 0. Therefore, we get 8 over 3 units squared. That is really messy units, but that says units if you don't believe me. So 8 over 3 units squared is the area underneath this curve. And you can see it's not a very big area. 8 over 3 is roughly 2 and 1, well, it's exactly 2 and 1/3. So 2 and a bit units cubed. That's because this graph is very enlarged. But you can just imagine, if you had to find this area without integration, this would be an impossible challenge, but integration makes it really easy to actually evaluate these. Now, this is a very basic case. We'll actually go to a more complicated case where you kind of just split up your area into multiple parts now. Now, here's an example of a more complicated area where you can see we have portions that are above and below the x-axis. And you might be thinking, can't I just apply the same formula? Or have you lied to me? Is this the wrong formula that you've told me? Technically, it's not the wrong formula, but this is a more complicated case where you're actually expected to get negative integrals or negative definite integrals because you have portions of the graph that are below the x-axis. If you remember with definite integrals, you can actually get negative values, and that's when more of the graph is below the x-axis than it is above. So what you can see in this case is that this part will be a negative integral, this part will be a positive integral, but for areas we always want positive values. So what you actually have to do in this case is split it up into its positive region and negative region, and then kind of add them together. Now, a lot of people, I'm just going to show you like the wrong way of doing it, just to emphasize, you're not meant to do this. You're not meant to do this way, but a lot of people would just go straight from 0 to 3 pi on 2 because they see, okay, that's the lower bound, that's the upper bound. My function is sine of x, and this is going to get me my right answer. No, that is going to get you the wrong answer. You don't want to do this way because, again, it doesn't take into account that this portion of the graph from pi to 3 pi on 2 is negative. So you might be asking yourself, how do you actually consider that that portion of the graph is negative? What you have to do is split it up into 2 areas. So we might call this one A1, we might call this one A2, and we just split it into 2 different expressions for now, just to make it a bit easier to understand. Now, A1 is the easy part, right? Because that's above the x-axis. So what we need to do is just a normal way of integrating from 0 to pi. So you just integrate this from 0 to pi, 0 the lower bound, pi the upper bound, and then we have sine of x dx. And we'll just leave that for now, we'll evaluate it later. Now a2 in this case, a2 is the portion of the graph from pi to 3 pi on 2 that's actually negative. So what we do is we actually make it the negative integral from pi, which is the lower bound, to 3 pi on 2, which is the upper bound. Now you might be thinking, why do we make a negative? It's because we expect this part of the expression, which is the integral from pi to 3 pi on 2, to be negative because it's below the x-axis. So what do we do to make a positive? We chuck a negative out the front, and that double negative is going to make a positive, which is going to find our absolute area, which is actually what we're trying to find. Now, you can see it's a bit messy. You've got the negative out the front, and negatives out the front is never a good thing in algebra because it makes everything a bit more complicated. So what we can actually do is we can keep it as negative and put lower bound to upper bound. That's perfectly fine. But what I like to do is I get rid of this, and I get rid of this as well. Sorry, my finger's smudging it. And I get rid of the negative as well. And what I can actually do is just swap the bounds. So put the upper bound at the bottom and the lower bound at the top. And what that's going to do is by swapping the bounds, it's going to induce a negative factor in our expression, and that kind of negates the need for a negative at the front. So I forgot the terminology, but that negates the need for a negative at the front because I've already swapped the bounds. And that means I just don't have to deal with the negative when I'm calculating my values. Now, what I like about these questions is that it reuses the same integral, so you can actually save a lot of the time that you spend evaluating things because the integral of sine of x is obviously not going to change, and you have some common substitutions, which makes things a bit easier. I'm going to change the pen color just to make it a bit clearer to read. Now, the integral of sine of x, you don't have to memorize this at the moment. Again, it's on the formula sheet, but with practice, you're going to know them all very easily. The integral of sine of x is actually negative cos of x. So I could take this as negative cos of x and then substitute my bounds of 0 to pi. Now again, as I said in the previous part, I don't like dealing with negative values because it does cause a lot of confusion when it comes to calculating things. So what I'm going to do is get rid of the negative and change my bounds here as well. And I can actually do it at this step as well. That's perfectly fine. I just have to make sure that if I do get rid of my negatives, I actually do swap the bounds as well. And I can do the same thing here. Once I evaluate this, I go negative cos of x first, just to illustrate it, and I will get rid of the negative once I've done it. So I can see here I've got a negative cos of x from 3 pi and 2 to pi. So I make this positive, get rid of this, 3 pi on 2 to pi. Again, I just got rid of the negative and I'll swap the bounds. It's going to make things a lot easier, trust me, when you're doing the calculation. And when I wasn't doing, year 12 methods, I always told myself, oh, I could just leave the negatives in, it's fine. But you don't understand how many times I got the answer wrong because I didn't deal with the negatives. And you get double negatives, and you see some of these cos substitutions will actually turn into negative values as well. It's going to make it even more confusing. You're going to have negatives upon negatives. It's going to be very messy, and you are going to get something wrong, I assure you of that. So just get rid of them. Don't be stubborn, humble yourself, and just make sure that you get rid of the negative values and swap your bounds, and it'll just make things a lot easier for you down the track. And you'll see now, when I get these negatives out, it's going to make things a lot easier because, for example, cos of 0 is just 1. Now, I don't have to deal with a negative value at the front. And then cos of pi is actually negative 1. If you imagine a unit circle, pi is there. You can see the x is the cos value, and the x value will be negative 1 at that left extreme of the unit circle. So this will be 1 minus negative 1. You can see, that's beautiful. 1 minus negative 1 is 2. If I left all the negatives from the start, I'm going to have negatives upon even more negatives. I don't want to do that. That's very simple. Now, this substitution here. Cos of 3 pi and 2. Where's 3 pi and 2 in the unit circle? It's there. What's the x value, which is the cos value in the unit circle? That's on the y-axis, so the x value just equals 0 for that substitution. Again, cos of pi is negative 1, so I end up getting that. So now I've got 1 minus negative 1, which is 2, 0 minus negative 1, which is 1. Therefore, I'm left with 2 plus 1, which is 3 units squared. Now, what we can see here is that this portion was 2 units, this portion was 1 unit, and you could kind of see some symmetrical properties here because 3 pi and 2 is halfway between pi and 2 pi, and 3 pi and 2 is just at that peak there. So yes, what I could have done is just calculated this portion here, multiplied it by 3, and I would have got the same answer. Now, with experience, you'll kind of know and see which functions are symmetrical or not. You can see that sine is symmetrical from the top to the bottom, same as coses, and same as you have even function, for example, if you have a parabola or anything like that. So in this case, what I could have done is just calculate that one area, multiplied it by 3. I could have calculated this area and multiplied it by 1.5. You'll notice all these, there's infinitely many ways that you can make this easier for yourself. So Figure out what works for you, make it simple for yourself, and you're going to assure that you're going to get the right answer. Now, in a previous video, we calculated the area bound by a function and the x-axis from an a to a b value, or a lower bound to an upper bound. We can get more complicated than that, okay? Things never stop in VCE methods. Things never stop getting more complicated in VCE methods, and it's an unfortunate fact of VCE, and specifically VCE methods. They try and make everything as hard as possible, and they try and add all these layers of complexity. But luckily, I'm here to help you try and solve this one. In this case, we're trying to find the area that's stacked between two functions. So in this case, we have f of x is equal to x squared, we have g of x is equal to x, and the shaded area, which is this black area here, is what we're asked to try and find. Now, if you want to make this really easy for yourself, you can memorize this formula, but it's really important to understand where the formula actually comes from as well. Because I'm a big believer in the fact that if you understand where something comes from and you understand the derivation, then it makes things a lot easier to actually apply. And it makes things a lot easier to remember as well, because you can think about where the formula is actually derived from, and you can kind of get that formula back for yourself. And this is a specific thing and a very niche idea that's actually not on the formula sheet, because this is kind of an application or an extension of what we know, which is area underneath the graph. So these types of things don't really have formulas in the formula sheet. So something that you have to kind of practice and also memorize at the same time. So let's get started with this one. The area in between two functions, just simply put, is the top function, or the integral of the top function minus the bottom function from the lower bound to the upper bound. And there's some things that we have to understand about this formula specifically. I mean, this is pretty obvious, but what is the top function and the bottom function? In this case, for this shaded area, g of x is equal to x, or that linear equation, is the top function. The red curve is the top function because it is physically stacked above the other one, which is f of x is equal to x squared. But just keep in mind that this is not kind of a cookie cutter approach, because you might have some other examples where you have some portion of the graph where one function is above, but then other portions of the graph, or the area, where the other function is above. So in that case, you have to split it up into two integrals the same way that we did if you had area above or below the x-axis. So you have to kind of split up the calculation into multiple areas. Don't worry about that yet. We'll do another example after this one. Now, easy. X is the top function, g of x is equal to x is the top function, the red, and then the bottom function is f of x is equal to x squared. But where exactly do we integrate from? What is the lower bound? What is the upper bound? That is something that we have to find through algebra. So in this case, what we do is we just find the intersections between the curve x and x squared. So we say x is equal to x squared minus x is equal to 0, x outside of x minus 1 is equal to 0, x is equal to 0 or 1. Cool. So it goes from x equals 0 up to x equals 1. So we have to find the y coordinates. No, because we don't need them when we integrate. So what we do is we say the area is equal to the integral from 0 to 1 of our top function, which is the red curve x, minus the bottom function, which is the green curve x squared. So we've got the integral from 0 to 1 of x minus x squared. And this is pretty easy to calculate. Pretty easy integrals here. X becomes x squared over 2. X squared becomes x cubed over 3. I expect you guys to kind of know where these integrals are coming from just by applying the formulas. I'm just going to rush it in this case it's not really the point of the exercise to practice the integrals, it's more so just understanding the concepts. Now substituting 1 and 0, this is the luckiest case because it's super easy to substitute in. 1 squared over 2 is obviously just 1/2, 1 cubed over 3 is 1/3, and then everything becomes 0 when you substitute in 0 into it. 1/2 minus 1/3 is just 1/6 if you convert it into its lowest common denominator. So we've got 1 over 6 units squared, and you might be thinking that is a super tiny area, 0.1 to 6666, 666 reoccurring, or just 1/6 if you want to put it simply. Now it's a really small area, by the way, but the reason why it's so small is because this graph is so enlarged. So this coordinate here would be 1, 1. This coordinate here would be 0, 0. So this is a really small sliver of that portion of area. So that's why the value is so small. Now we'll go into a more complicated example where we have multiple portions of our area that we need to split up into different integrals. Okay, so here we are with a pretty complicated example. We have the area that's bound or stacked by f of x is equal to sine of x and g of x is equal to cos of x. So we're trying to find that black shaded area. You can see from kind of x equals 0, the y-axis, to that intersection there, the red curve is above the blue curve. But then from that intersection to the second intersection, we have the blue curve above the red curve. So that's how we split our area or our integral equation up. We have that portion, that's where the red curve is stacked above the blue curve, and then the second portion is where the blue curve is stacked above the red curve. So the first thing we have to do is figure out where those bounds are for each of those integrals. And the only way that we can do that is by solving f of x is equal to g of x and finding those intersections. So in this case, f of x is equal to sine and g of x is equal to cos. So we just say sine of x is equal to cos of x. And you can kind of see that this is for one cycle, and yeah, we can just solve this when 0 is less than or equal to x, which is less than or equal to 2 pi, or pretty much just the first rotation or the first revolution of these circular functions. Now, a lot of people see this and get kind of confused. Oh, I've got a sine, I've got a cos, what do I do? You just divide both sides by cos, because what that'll do is you get sine over cos on the left side, which becomes tan, and then you get cos over cos on the right side, which obviously just becomes 1 because they cancel out with each other. So what we're doing is we're just solving tan of x is equal to 1 for the first cycle. Now you can go through the whole rigmarole and try and solve it. I'll just tell you that the solutions are in the first and the third quadrant because that's where tan is positive, and they're just going to be pi on 4 and 5 pi on 4. You can do the long way if you want, but for this question, the point of it isn't not the trigonometric solving, it's actually applying our area between two curves kind of formulas and our concepts. So you can see this part is going to be pi on 4, this value here is going to be 5 pi on 4, and that is obviously x is equal to 0. So I'm just going to write them in. So this is pi on 4. I'm going to break my rule and not put the coordinates because they do not matter in this case. It's kind of just more for our reference. Sweet. So what we're going to do is split it up into two areas. We've got, maybe we'll call this one A1, this one A2. So A1 is going to equal the red curve minus the blue curve, so sine minus cos. So the integral of that, sine minus cos dx. Now what are our bounds? Lower bound is 0, upper bound is pi on 4. Pi on 4, sweet. A2 is going to equal the blue curve minus the red curve. I think I actually got that one the wrong way around. Oh, cooked it a bit. Yep, okay. So cook that one, cos of x minus sine of x, because it is the red curve minus the blue curve for the first portion. The other one is going to equal the blue curve minus the red curve, which is sine minus cos dx. And this one is going to be from pi on 4 to 5 pi on 4 as our lower to upper bound. Now we can evaluate all these, so we can just say the total area is going to be equal to A1 plus A2. So A total is going to equal the integral of cos minus sine. So integral of cos is sine. Integral of sine is negative cos, so we're minusing negative cos, which becomes a positive cos. It's going to be plus cos of x, and that's from 0 to pi on 4. Now our other integral, sine, integral of sine, what's that? That becomes negative cos. And integral of cos, that becomes positive sine, but we're minusing it, so it becomes negative sine of x when we do our final calculation. That's from pi on 4 to 5 pi on 4. Hopefully this is still in view. I think it is. Now, you can see that this one is fully negative, so what I can do is just remove the negatives, make that positive, and I could also swap my bounds as well. So make the top bound pi on 4, try and get it as efficient as possible, just rubbing out the 5, and I'll add a 5 to the bottom one. Again, getting rid of the negatives is a life changer. Now, let's just do our substitutions. Now, sine of x, when we substitute in pi on 4, sine of pi on 4 is just root 2 on 2. I can write as 1 over root 2 as well, but I prefer to keep it rationalized. Cos of pi on 4 is actually the same, root 2 on 2. And then our minus sine of 0, which is 0, plus cos of 0, which is actually 1. Don't get this cos of 0 is equal to 0. A lot of people do that, a lot of my students do that, and it's because they just see, okay, cos of 0, it's going to be 0. Cos of 0 is actually 1, because it's the x value when the angle is 0 on the unit circle. Now, cos plus sine of x for pi on 4, it's exactly the same as this substitution here. So that was root 2 on 2 plus root 2 on 2. Now, we minus the substitution of 5 pi on 4. This is where it gets a bit more confusing, so I'm just going to draw the unit circle. 5 pi on 4 is in the third quadrant, and actually in the third quadrant, both sine and cos are both negative. So what's actually going to happen here is we're going to have negative root 2 on 2, because when we simplify that angle, it ends up becoming pi on 4. So it'd be minus root 2 on 2, minus root 2 on 2. Now I like the sign of this, because we can see that there's a lot of square root of 2's, which makes it a lot easier to simplify. So square root of 2 on 2 plus square root of 2 on 2 is equal to just square root of 2 by itself. I'm just going to make this square root of 2. And it's the same for all these ones as well. Square root of 2. I'm going to use a different color actually. So this one becomes square root of 2. Oh my goodness, that's even worse. Square root of 2. Square root of 2. Now we're minusing the same thing. We're minusing the minus of that, so the negatives cancel out. So this one will become square root of 2 as well. So that's really messy, but hopefully you guys can see that this one becomes square root of 2, and then negative of a negative square root of 2. So we end up having 3 square root of 2's minus 1. And that will be unit squared. Don't forget the unit squared for area, and that'll be our final area for this stacked integral. And you can see that this one is very messy, because whenever we have sines and coses, it always gets confusing, because sines become coses, coses become sine, and it just gets really messy because you have a lot of trigonometric terms and you have a lot of angles to substitute in. But hopefully you can see if you break it down and get rid of the negatives, I really emphasize that, getting rid of the negatives. If you get rid of the negatives and break it all down into its components, it actually becomes a lot easier. And in this case, you have a lot of common terms that you can actually combine together. So you can see here, I try to keep everything in terms of a common denominator to make sure that, it makes it a lot easier to combine terms and substitute things in. And you can see here, if I just recognize that these are all the same brackets, it makes everything a lot easier in the long term. Finding areas in VCE methods may seem really easy at first, but what the examiners and your teachers like to do is make it infinitely more complex than it has to be. And here's an example of one where this has actually been asked on past SACs and past exams, and it's where your area may not be as easy to calculate as it first seems. In this case, we have a log curve, and the shaded area that we're asked to calculate goes from x equals 1 to x equals 3. And at first glance, what a lot of students would do is try and integrate log, but the problem is that the integral of log is actually not in the course, it's not on the formula sheet, and it's something that we actually not expected to memorize. So if you have a tech-free exam where they ask you to find the area of this shaded region here, it would actually be very hard to find and almost impossible by trying to find the integral of log. Obviously, it's a bit different if you have your calculator. You'd probably be able to find a rule or an expression for the integral of log, but in this case, we actually can't. So we have to be creative and think about how else we can find this area here. Now, what we do in this question, I'll just give it away because obviously you're here to look at how to do these types of questions, and hopefully it gives you a bit of exposure to more creative problem-solving techniques, is actually recognizing that we do know a lot of information about this curve, and in particular, if we find the inverse of this curve, we actually know a lot about that function, and the inverse of log e of x we should know is y is equal to e to the power of x. Obviously, if I just swap x and y, I can rearrange and I get y is equal to e to the power of x. So I'm going to draw this on the same graph just to illustrate, what that looks like and how it relates to our original function of y is equal to log e of x. So we should know that inverse functions and the original functions are symmetrical about the line y is equal to x. And more importantly than that, your coordinates actually swap our locations. So for example, if this is y is equal to log e of x and we have an x-intercept at x equals 1, then this function actually has a y-intercept at y is equal to 1. And if we want to reflect this area as well, go further than the coordinates, but also the area as well, we know that the shaded region, it might not be the same shape because I've drawn it kind of badly, but this area should go from y is equal to 1 to y is equal to 3. So this is the same area, so the black area is the same as the blue area, it's just reflected, and we know a lot more information about this curve, namely the integral, more so than the green curve, which is y is equal to log e of x. So this is y is equal to e to the power of x, and that's the area that's equivalent to the blue area. So now it's just a matter of finding this area and making that equal to this. So how do we find the black area? What we know is that when we find the integral of something to find the area, it gives us the curve that's the area that's underneath the curve and bound by the x-axis. So let me just get a new color. If I integrate this, what happens is that this area here will be calculated, and if we integrate from here to here. So what we have to do is just find that red line there. We know that the starting integral is 0, well, x equals 0, so we just have to find that point there. That's kind of easy to find. All we can do is just say 3 is equal to e to the power of x. Therefore, x is equal to log base e of 3. So therefore, this coordinate here has an x value of x is equal to log base e of 3. Now, if I wanted to find the red area, what I do is I just integrate y is equal to e to the power of x from x equals 0 to x is equal to log e of 3. Now again, that kind of gets us one step closer to what we're trying to find, which is the black area. All I have to do once I find the red area is find the area of the big box. Again, I'll use a different color. So I'll find the area of the box here, and I'll minus the area, the red area, and that's going to give us my full area or my remaining area, which is black. Now, just to reiterate, if I want to find the goal area I have to find that full blue region, which is the rectangle, and then minus that red region. And I know how to calculate both because I have enough information to do so. And I didn't have enough information when I started this question because it was just a log curve, which I don't know the integral of. So what we do is we just calculate these two things and find the difference of them. So the blue curve, that's really easy to calculate. It's just the area of a rectangle. So what we do is the x value is log e of 3, the y value is 3. So therefore this area here is 3 log base e of 3. Now the red area is a bit harder to calculate. It's just the integral though of e to the power of x, and that goes from x equals 0 to x is equal to log e of 3. So 0 log e of 3 dx. So I'll just go ahead and simplify this. So 3 log e of 3 minus the integral of e to the power of x. Very easy, hopefully you don't forget this one. It's just e to the power of x. And that goes from 0 to log e of 3. 3 log e of 3, and then I substitute this in. So I end up getting e to the power of log base e of 3 minus e to the power of 0. Pretty easy, e to the power of 0 is 1. E to the power of log base e of 3, the e's and the logs are kind of opposite, well they're inverse functions, but they actually cancel each other out algebraically as well. It's the same as x squared to the power of 1/2. We know those things combine and cancel each other out. In this case, exactly the same thing, so we're just left with 3 for this expression here. So therefore, and it's 3 log e of 3 minus this whole bracket here. So it ends up being, when we expand this, it ends up being minus 3 plus 1. So we end up getting 3 log e of 3, bit of a tongue twister, minus 2 units squared. So that's that black area there, that little quadrant there, and that's the same as the blue area here due to our reflection properties with our inverse functions. Apart from finding the area underneath a curve, there are a lot of smaller applications for integration. One of the main ones is finding the average value of a function. It's pretty self-explanatory what that essentially means, but essentially it's just the average level of a function, and it takes into account the negative and positive regions as well. So the formula for it is the integral, the definite integral of the function from a to b, a lower bound, b upper bound, but then we divide by the difference between the lower and the upper bound. So we have this example here where we have f of x is equal to x squared minus 1/2. And I've used this example specifically because you can see from x equals 0 to x equals 1, that's what we're trying to find our average value for. But you can see the y value at the lower bound is negative 1/2, the y value at the upper bound is positive 1/2. And I've used this example on purpose because a lot of people would see this and think that the average value is going to be 0, because you can see the midpoint between negative 1/2 and positive 1/2 is obviously 0, or at the x-axis. But in this case, you can't actually do that because now we're kind of confusing midpoint and the average value, which is slightly different. And I'm going to show you with calculations that it is different and then explain why. So if we want to find the average value of this function, what we do is we just apply this formula here. So we go 1 over and then 1 minus 0 because they're our x bounds. The x upper is 1, x lower is 0. Don't confuse it with the y bounds. And then we go integral from 0 to 1 of x squared minus 1/2 dx. And then we just go ahead and evaluate this. Obviously the 1 divided by 1 minus 0, that has no effect in our equation, so that makes it a bit easier. And then we don't need integral anymore. We just go straight to definite integral. X squared becomes x cubed over 3. 1/2 becomes 1/2 x. 0 to 1. And again, 0 to 1, very nice numbers to substitute in when we're doing definite integrals. So we go 1 cubed over 3, and then minus 1/2. And then when we substitute in 0 to everything, we end up getting 0. So our final answer is 1/3 minus 1/2. If you want to do this the long way, you make a common denominator. So you go 2 over 6 minus 3 over 6, which is negative 1/6 as our final answer. And you might be thinking, oh, we have a negative value. What essentially does that mean? Or what exactly does that mean when looking at our curve and the properties of it? And you can see in this case that, yes, a lot of people would see the midpoint as y is equal to 0 and think that's our final answer. But in this case, what you can actually see, if I change colors, is that this area here, or like the density of this curve, is lower than this curve here. And that's just due to the nature of our parabolic curve. We know a parabolic curve goes something like this, where you start off more shallower, and as you go further and further, you go steeper. And that's just due to the squared nature of functions. Because you can imagine, if we just look at a basic case of a hyperbola, we start off at 0, 0, then we go through 1, 1, and we go up from there. And actually this is, again, basic case, y is equal to x squared. If we go from x equals 0 to 1, what you can see is that the curve is actually very shallow, and that's because when you square a number that's less than 1, it actually gets smaller. So for example, if you do 0.8 multiplied by 0.8, you get 0.64, which actually causes the number to be smaller. But if you go beyond x equals 1, for example, if you go x equals 2, you square that number, it actually gets bigger. And that's what causes the parabolic nature of this curve here, where it goes shallow at the start and steeper at the top. And you might be thinking, what does that have to do with my average value? It's because if this curve is shallower at the bottom, there's more numbers here than there are here. And that actually causes the average value to be less than y is equal to 0, or less than the midpoint. It's because the midpoint is here, but you can see the curve is kind of lower compared to how high this curve is here after the x-intercept. And that's why in this case, or in most cases, the average value is going to be different than the midpoint. Integration by recognition is one of the harder topics that's in integration, and honestly in the whole VCE Methods course, because it's something that a lot of people don't fundamentally understand how it works. But if you understand how integration by recognition works, you'll be able to apply it in any sort of situation. So what I'm going to do is talk about the most basic integration by recognition example, and then kind of expand on that with more progressively harder examples. So in this case, what we're going to do as an exercise, without thinking about integration by recognition or any of those steps, is we're going to try and find the derivative of x squared, and then from that we're going to try and find the integral of x dx. I'm going to show you how these things relate. You should already be kind of preempting how they relate, and it's because integration and differentiation are opposites. And a lot of people forget that when doing integration by recognition, but it's a really important concept to get your head around before we actually do integration by recognition, because that's the key step in order to execute things. So what we do here is we find the derivative of x squared. We know we multiply down by the power and then minus 1 from the power. We know this becomes 2x. Now, you might be thinking, how does this integral, the integral of x dx, relate to the result that we got above? And the reason why it relates is because this statement here is exactly the same as this statement here, just a rearranged version of it. Because we know, again, that differentiation is the opposite of integration. So the integral of 2x with respect to x is equal to x squared plus c. Now, if I know this is true, what I can do to find the integral of x is just divide this expression, and hence this expression, by 2. So therefore, the integral of x dx is just going to equal x squared on 2 plus c. Now, we could already calculate this. We already know that this is the case because we have integration rules that tell us that this is true, namely the power rule that we use for integration. Except there's a lot of integral rules that we don't necessarily know from the formula sheet, but with integration by recognition and using an appropriate derivative, we'll be able to find the appropriate integral. And we'll go through an example of that now. Okay, so now that we talked about a really basic example and how integration by recognition actually works, let's go to an example where we can actually find the integral of something that we don't know from the formula sheet. So in this example, we have two different parts. The first part tells us to find the derivative of x multiplied by log e of x, and then based on that answer, that's kind of given away to us through the word hence, it asks us to determine the integral of log e of x. So let's just have faith and do the first part and hope that the second part actually relates to the first part. And obviously, because this question is structured, it obviously is. So if we find the derivative of x log e x, we just use the product rule. So if we wanted to find this very easily, what we do is we say that this is u, this is v, so therefore this is going to be equal to u v dashed plus v u dashed. So the derivative of x is 1. So we get log e of x, and then the derivative of log e of x is 1 on x. So it'd be plus x multiplied by 1 on x. So we end up getting log e of x plus 1 as our derivative. And just keep in mind, this is d dx x of log e of x is equal to log e of x plus 1. I'm actually going to write that statement here because that's going to help us with the next part. X is equal to log e of x plus 1. Sweet. Now, for part B, determine the integral of log e of x. The key step in this case was the same as the key step in the previous case where we had x squared becoming 2x. We just have to write this in its integral format. So the integral of log e of x plus 1 is equal to x multiplied by log e of x plus c. Essentially, I'm just going to get a different color. This, which is what we derived, comes here. And this, what we differentiate in the first place, goes there. And it's pretty obvious. You just integrate the derivative that we got, and we get our original function back. Now, we know the integral of log e of x plus 1 is equal to this, and we're trying to find the integral of log e of x. So it makes sense that we're trying to get rid of this 1 here. So this plus 1 here, it's kind of a nuisance. If we get rid of that, we get the integral of log e of x. Now, how do we get rid of that? A lot of people would see this and just want to minus 1 straight away to the other side. But we actually can't do that in this case, and that's because the plus 1 is underneath the integral, or within the integral. So what we actually do is we split up this integral into 2 separate ones. So we've got the integral of log e of x dx plus the integral of 1 dx. And when you see that, you can actually see that we have to integrate 1 before we move it to the other side. X plus c. Now if we integrate 1, what do we get? We know that that becomes x. So what I can do is therefore say that the integral of log e of x is equal to x multiplied by log e of x minus x, because that's from there, moving it to the other side, and then plus c. Sweet. One last thing before we forget, this is where a lot of people would stop the question, right? Now this is technically correct. This integral is technically correct. The integral of log e of x is equal to x multiplied by log e of x minus c. Minus x, sorry, plus c. Now, a lot of people would overlook this, but you can see plus c, plus c, plus c on every line. That's perfectly fine, right? But the problem is that the c here is fine, whatever, that's just part of an integral, right? The c here is also fine because nothing changed on the right-hand side from this step to this step. But then from this step to this step, we actually expect the c to change because we moved an integral to the other side. Because this x here, this integral of 1, which became x, that's going to have its own constant of integration, okay? So when it has its own constant of integration and we move it to the other side, we expect the c to change because the constant of integration is going to affect the other one, right? You essentially combine them together. And a way of imagining it is we can imagine the integral of 1, we could write it as x plus, let's say, c2, and then we move that to the other side, the constants combine together and change. So what I do to kind of remedy the situation is I make this step c1, and then, as I said before, the c doesn't change from step 1 to step 2, but then from this step to this step, it's got to change, okay? So that's why I change this to c1, but I leave this as c just to signify that it's changed from the second last step to the last step. Kinematics is one of those things that a lot of people don't want to do and a lot of people don't want to learn because they think it's just a physics thing and physics students have an advantage. Luckily, I'm here to teach you how to do it very simply. In VCE Methods, physics doesn't go that deep. It's mainly modeling kinematic equations, which involves acceleration, velocity, and position. Now, in this pretty basic example, we have a ball thrown vertically at, I've kept it blank, should be 25 meters per second squared, meters per second of a 30-meter tall building, and assume that gravity is 10 meters per second squared. So in this case, what we should do is illustrate what's actually happening. So we're going to draw the building here. This building is 30 meters tall. The ball is thrown vertically at 25 meters per second. Okay, and gravity is 10 meters per second squared. Obviously, this depends on the question as well. Sometimes gravity might be said as 9.81, sometimes it might be 9.8. In this case, it's 10 because it is a tech-free question, and it's easier if you have 10 because usually the numbers work out a lot better compared to if you had 9.8 or anything like that. Now, for this type of question, what we have to do is kind of interpret all the information or absorb all the information in the question. And it looks like we've done that vertically, 25 meters per second, 30-meter tall building, and gravity is 10 meters per second squared. So firstly, we're asked to determine acceleration. Acceleration is pretty easy. It's already given to us, but a lot of people kind of overlook this because they kind of see acceleration as something different. But when something is kind of thrown vertically and there's no external forces applied to it, then the only acceleration comes from gravity. So what we can say in this case is A of t is equal to -10. And I'll just include a unit as well, which is meters per second squared. Now, I just want to reiterate that this negative sign and where your kind of relative position is dependent on what you define. So for example, in this question, I've said up is positive. I've kind of assumed that up is positive and downwards are negative. It kind of makes the most sense, right? Because upwards positive, downwards negative. So when I put acceleration, I'm putting it as negative because I want to indicate that gravity goes downwards. And you can see here, even though it has g is equal to 10 meters per second squared, just by default, it's using the positive value because, you know, it's a constant, right? So it's not going to include the negative value there. I mean, it may or may not, depending on how the question's written, but we should know that gravity as convention is negative. So this one has to be interpreted as going downwards, so therefore I've included the negative. By the way, you could include upwards as negative if you wanted to, and downwards is positive. It's up to you, right? So it just depends on how you define your question. Cool. And it's not only how you define your question, and it's also about like keeping everything constant as well. So you'll see for the next one, right? When I put v of t we should know is just the integral of a of t. And now if I integrate -10, I get -10t plus c. Now my initial velocity, I already know, is 25 meters per second. And this value here, I'm going to include as positive because it's thrown vertically upwards, right? Because I've defined upwards as positive, downwards as negative. So that's what I mean when I say you have to keep everything consistent. So in this case, velocity should be equal to -10t plus 25 meters per second. Okay, and you should see a correlation between these units, meters per second squared, meters per second, and then when we get position, it's going to be just meters. So make sure that you keep your units consistent as well. And the most common unit that's used in VCE methods and just in VCE in general is meters and seconds, because they are what we call SI units, or the standard units that are recognized internationally. Next question, determine the position, or x of t. So in this case, it just goes one step further with velocity. So we say x of t is equal to the integral of v of t. So integrate this, we end up getting -5t squared plus 25t plus some sort of c value. In this case, what's the initial position? Well, it depends what we use as our reference plane. In this case, the reference plane makes sense to be ground. So this could be ground is equal to 0. So where do we start from? We start from here, which is 30 meters upwards. So our c value should be +30. Again, this is not the only right answer. It depends on how you define your question.